Hello, good people. Today we are talking about the concept of torque. Now, so far, everything that we have done in this unit has been things that are moving at constant speeds in what we call uniform circular motion. So you have something that is spinning, but it's spinning at a constant speed, not speeding up or slowing down. Well, today we're going to talk about things that are speeding up as they spin, slowing down as they spin, or starting spinning when they weren't spinning before, or stopping spinning when they were spinning before. Today we're talking about the concept of torque. Now I got two definitions of torque for you. The first one is torque is the tendency of a force to rotate a body. And my second definition for you, first one, torque is the tendency of a force to rotate a body. Yes, do write it down. And the second one is that torque is what makes an object speed up spinning or slow down spinning. Torque is what makes an object speed up spinning or slow down spinning. Now, I like to start by giving the equation for torque. So I'll give you the equation for torque, and then we'll talk about what it means. We'll see that there are actually a lot of vocab words that are kind of embedded in this equation. First, if we're going to use a symbol for torque, we are not going to use the capital letter T or the lowercase letter t, because lowercase letter t means time, and capital letter T means both period and temperature, which is not what we're going for here. So instead, we'll use the Greek version of the letter T, which is the Greek symbol tau. It's like a backwards letter J. And instead of a regular T with a flat hat, it has a swoopy hat. And we say that torque is equal to the force that is parallel to the lever arm times the length of the lever arm. And you need vector hats on all three of these quantities. Do add this equation to your bag of tricks. We'll start by defining the units here. The units of torque are the units of force, which is newtons, times the units of length, which is meters, and so the units of torque are newtons times meters. Now, torque is what causes an object to spin. If it's not spinning, it's what speeds up the spinning of an object that's spinning, it's what slows down the spinning of an object that is spinning, or it's what stops an object that is spinning. Now, I'm going to start by looking at a little example here. We're going to start with an example of, suppose that you had a bolt here, like this. This is a top view of a bolt. And suppose that you had a wrench and that you wanted to loosen this bolt. Now, initially, if this bolt is just sitting here, it is not spinning. But if I have whoa, that is not what I want here. Let's try, wait for it. Okay, you can do it. Okay, here, let's try this. That's not very good, wait. Sorry, I'm so sorry. I get so perfectionistic. Okay. It's not great, but that'll do the trick. Okay, suppose that I have a wrench like this around a bolt, like this. Now, if I want to turn this bolt is currently not spinning. If I would like to cause this bolt to spin, then I am going to need to apply a torque. To apply this torque, here's what I'm going to do is I am going to apply actually I'm going to go green here. I'm going to apply a force here to the end of the wrench, and that force, when I apply it, is going to make the wrench and the bolt together spin. Now, there are a few key little vocab-y things that we have to talk about here. First, right here, this is the point that bolt is going to spin around. This point that the bolt spins around, actually I'm going to do this in pen so that it's nice and small. This point that the bolt spins around, this is what we call the axis of rotation, or sometimes we call it the pivot point. Or sometimes we call it the fulcrum. All three of these words can be used in slightly different ways. There are slight nuances between the three of them, but we will use them somewhat synonymously. It just means the point that the object is going to spin around. So we call it the axis of rotation, the pivot point, or the fulcrum. It's what that object is going to move around. Then, the place where the force is applied, which in this case is right here, we call the place where the force is applied the line of action. So my pivot point is here. That's what the bolt is going to spin around. My line of action is here. That's where I apply the force. And my last little vocab term here is going to be the distance from the pivot point to the line of action, this length right here. This length, which starts at the pivot point and ends at the line of action, this is what we call the lever arm. And we represent the length of the lever arm with the letter L like this, and it's a lowercase cursive e letter L. If you want to find the size of the torque that's applied to this bolt here, the size of the torque would be the force that you applied to the end of the wrench times the length of the lever arm. And that is the torque that will cause this bolt to move. To find it, you just multiply these two values together. Now, something that you'll notice here is that you're looking for the force that is parallel to the length, not parallel, perpendicular to the length of the lever arm like this. Suppose that instead of applying a force like this, suppose that I applied a force like this. If I apply a force going this way, that is not going to make this bolt turn. It might make the bolt accelerate this way, but it's not going to make it go in a circle. If you want something to go in a circle, you have to apply a force that is perpendicular to the lever arm. Do you see that the only way to make this guy go in a circle is to either apply a force down like this or up like this? A force like this would not make this thing turn. Now, one thing that I could do is I could apply a force at an angle like this. If I apply a force at an angle like this, well, then do you see that there is actually a component of this force here that is parallel to my lever arm, and we'll call this F parallel. Then there's a component of this force here, like this, and this is the component of the force that is perpendicular to the lever arm. If I defined this angle here to be the angle of my force, we'll call it angle theta, and I asked you how much torque is being applied by this force, well, you'd say the amount of torque that's being applied by that force is the part of the force that is perpendicular to the lever arm. You would say the part of this force that is perpendicular, that's not the whole force. That is just F times the, careful here with your trick friends, sine of theta times the length of the lever arm L. A lot of times your textbook will say that torque is equal to the force times sine of theta times L. Now, that is true in most circumstances, but what I like to say instead is I like to say that torque is equal to the force that is perpendicular to the length of the lever arm times the lever arm. And showing this equation, then I look at my picture, I figure out where my angle theta is, and most of the time the perpendicular component will be this will be sine of theta, but not all the time. So I say I'm looking for the perpendicular part, I draw a picture, I see where my angle is, and that helps me figure out where is my angle going to be here and where am I going to use sine or cosine. So there's one example of a use of torque. Let's take a look at another example. Suppose that I go to a door and I push on the door handle and I open the door. If you open the door, you're creating some torque because before that door was just sitting there, but now the door is moving and it's actually spinning around its axis. I'm going to show you a picture of a door here. This is a picture of a door from a bird's eye view. So this is just like the top of the door here. It's nice and skinny like the top of a door would be. Here's where the hinges are, is right here. And here I'm going to draw a little doorknob right here so that if a bird was looking down, they would see here's the axis, or here are the hinges, here is the doorknob, and here's the door. Can you, on your diagram of your door, label where would we have the axis of rotation, or the pivot point, where would we have the line of action, and where would you have your lever arm? For the door, I would say, okay, well, let's take a little look here. I would say that my, let's go light brown. Well, this isn't really light brown. What is? Oh, it is light brown. That's what they call it. Okay, yeah, we're going to go with brown 500. Let's say that if looking at this door, I would call this right here, I would say that this is going to be my axis of rotation. or my pivot point is going to be where the hinges are, because that's going to be what the whole door spins around. I'm going to say that my line of action, that would be right here. I'm going to apply a force to the door going this way, and so that's going to cause it to rotate. So here is my force that I would apply to the door. That makes this line right here my line of action where the force is applied. The length of my lever arm then is the distance between my axis of rotation and my line of action. This right here is the length of my lever arm L, like so. Now you can see from our equation here that there are two ways to increase your torque. You could either increase the force that you apply, or you could increase the length of your lever arm. If I want to open the door faster, I could apply a bigger force, and that would cause it to go from not rotating to all of a sudden rotating much faster. Or I could increase the length of my lever arm. You've noticed before that all door handles are as far away as possible. They're on the opposite side of the hinges of the door. Why is that? Well, if you had some door handles, we'll just draw it here in this color. If I had a door handle right here, I could most definitely from here apply a force if I wanted to. But if I apply a force here, do you see that then the length of my lever arm would be tiny? And so it would give me a very, very tiny torque. That door would be very, very hard to turn, because I would need to apply a lot more force since my lever arm would be teeny, teeny, tiny to get the same amount of torque. But no, we put the handles on the other side. It makes it easier to open the door. Why? Because the length of my lever arm is so long that it means I need less force in order to get the same amount of torque. Let's look at one more example here that's a little conceptual, and then we'll talk about net torque and equilibrium. Suppose that I have a screwdriver and a screw, and I'm just trying to get that screw unscrewed, and it's just not budging. It just will not move. Let me show you a picture of what we're looking at here. We got, let's have a green screwdriver. That sounds fun. Okay, here is my screwdriver here like this. Let's go. Wait. Sorry, team. You guys are oh so very patient. Let's go long here and long here like this, and then like this. And that screwdriver is going to go down into a little screw like this. There is my screw. Okay. So there it is. Here's my screwdriver and my screw. Now here's a question. Suppose that I am turning and turning and turning the screwdriver and that screw just won't budge. Do I want a screwdriver in order to help me out? Do I want a screwdriver with a longer handle, a screwdriver with a shorter handle, a screwdriver with a skinnier handle, or a screwdriver with a fatter handle? What will be the most helpful to me? Well, first let's take a look at this picture and let's identify some things here. First, the axis of rotation. This one's pretty simple. To find the axis of rotation is going to be straight through the center of the screwdriver like this, because that's what this whole thing is going to be spinning around. So this here is my axis of rotation. Then, suppose that I asked you, where is going to be my line of action? Well, this one is a little bit trickier. Here's what a lot of students will say. A lot of students will say, oh, well, up on the top, Miss Wilson, that's where you apply the force. But that's not true. If I want this thing to turn, what I actually have to do is I have to apply a force on this side of the screwdriver here that is going away from me, and I have to twist this screwdriver so that this side is coming out towards me. So I want this side to be going away from me, and I want this side to be coming towards me. That's where I apply the force, is on the sides of the screwdriver. So my line of action is right here and right here on the sides of the screwdriver. That means that my lever arm goes from the axis of rotation at the center of the screwdriver to where I'm applying the force on the sides of the screwdriver. So this right here, this is my line of action L. And I have another line of action here on the other side where I apply a force going towards me. This is my other line of action L. If I am applying a force and that force is not big enough to get it to budge, then I need to increase the length of my lever arm. To increase the length of my lever arm in order to increase my torque to get this screw to budge, I want a fatter handle here. Those are a few examples of some different torque situations where you have something that is not spinning, that you cause some spin by applying a force times a lever arm. But now we're going to do a little bit of it'll be both conceptual and mathematical, some work with what we call net torque. The same way that we have net force, we can also talk about net torque. Net torque is the sum of all of the torques acting on an object. It's the sum of all of the torques acting on an object, so you can add them all together. Just like how we talk about with Newton's laws when we talked about forces, we talked about how you can have a state that we call equilibrium. And we said equilibrium is a state in which the net force is equal to 0. For torque, equilibrium is a state in which the net torque is equal to 0. If you have a state of equilibrium, an object that is spinning will not speed up spinning. It will not slow down spinning. It'll keep on spinning at a constant velocity. That means that the net torque is 0. If you have an object that's not spinning, an object that is not spinning will keep on not spinning if it's in a state of equilibrium. Let's try a little bit of a practice problem here. Suppose that Jimmy and Timmy go to the park to play, as brothers often do. And suppose that Jimmy says to Timmy, Timmy, can we please, pretty, play on the seesaw? And Timmy, being the good older brother that he is, says, okay, Jimmy, yes, we can go play on the seesaw. And Jimmy says, yay! And they both get on the seesaw here. Here's my seesaw. Suppose that we have Timmy standing over here on this side of the seesaw. Here is Timmy. And suppose that we have Jimmy standing on this side of the seesaw over here. You could tell that Timmy is quite a bit older than Jimmy. In fact, at this point in their little lives, Timmy happens to have twice the mass of Jimmy. So we know already that the mass of Timmy is 2 times the mass of Jimmy. Now, before we really get into this problem, let's take a look here. Do you agree that both, wow, why do I have a wheel of death right now? What is even loading? Okay, that is exciting. Okay, do you see that Timmy is going to try to create a torque on this seesaw? Timmy is going to try to create a torque on the seesaw that makes it turn down this way and around this way like this. This is going to be the torque created by, whoops, there we go, swoopy, created by Timmy. Meanwhile, Jimmy is going to create his own torque. He's going to create a torque that tries to make the seesaw turn this way, like this. So both Timmy and Jimmy are going to create a torque on the seesaw. Now, you have noticed that we have been writing torque with these vector hats here. And there's a reason for that, because torque does in fact have direction. When we talk about the direction of torque, we traditionally say that a positive torque is clockwise, that a positive torque is counterclockwise and that a negative torque is clockwise. Let me show you why we say that here. You know the good old traditional Saxon axis. On the good old traditional Saxon axis, we say that this is my x and this is my y. And if I asked you, hey, which way would you want to go around this axis if I was saying going in the normal positive forward direction? You would say, oh, well, the normal direction around this axis would be starting here and spinning around just like this. And I say, yes, that is the counterclockwise direction. And so we shall call that direction positive because that's the normal way around. But then if I asked you, hey, can you go around this guy backwards? You would say, backwards? Yeah, for sure. You would start here and you would go around back this way. And we would say, yes, that is the negative direction. That's the negative way to move around the circle. And that is the clockwise direction. So it is tradition to say that counterclockwise is positive and that clockwise torque is negative. So when you're looking at this picture of Timmy and Jimmy, can you say who has clockwise torque? Let me try again. Who has positive torque in this situation and who has negative torque in this situation? Yes, you should say, well, Timmy over here, he's going to be the one who has some positive torque, and Jimmy over here is going to have some negative torque. Now, here's a question for you. Right now, whose torque is going to win? Timmy's torque or Jimmy's torque? You say Timmy is going to win because Timmy has more mass, and so he's going to apply a greater force, and so he's going to experience more torque, and the whole seesaw is going to go, and, well, I guess, wait, is that right? Oh gosh, the screen's always backwards from the way that I'm seeing it, or my video camera's always backwards. So, Timmy is going to make the whole seesaw go down, and Jimmy's going to go up to the air. Well, that is really fun for all of about half a second, and then Jimmy says, no, Timmy, this isn't fun anymore because your torque is bigger than my torque, and so you are winning, and I would rather have a more fair game. Here's a question for you. If Timmy wants to have a more fair game, what could Timmy do? Well, you say, Miss Wilson, it's simple. You say, take a look here, Miss Wilson. This right here, this point is our fulcrum. It's the point that the whole seesaw is going to turn around. Whoa, we got a W in fulcrum. Fulcrum, yay. Okay, that's the point that the whole seesaw is going to turn around. Now, we would say that Timmy is going to create a force down on the seesaw, and that force down is going to be the force that Timmy applies, which is going to be equal to Timmy's weight. Meanwhile, Jimmy is going to create a force down on his side, and the force of Jimmy is going to be equal to Jimmy's weight that he applies downwards on the seesaw. Then, let's look at their lever arms. If this is our pivot point, and here's one line of action and here's another, then we got two lever arms. This first lever arm here is the distance from the center here, this fulcrum point, to Jimmy. It's this distance right here. We would say that this is the length of Jimmy's lever arm. Meanwhile, we would say that Timmy has his own, oh gosh, wow, sorry, I guess my pen just really likes to fly. Jimmy has his own lever arm like this, which is the distance from the fulcrum point to the line of action, and we call this the length of Timmy's lever arm. Well, here's the idea. Jimmy says, can you lessen your torque just a little bit by stepping forward? Because if you decrease the length of your lever arm, Timmy, then we could actually be evenly matched. And Timmy says, I agree, but you must tell me, Jimmy, where exactly shall I stand in order to match our torques so that our torques are the same? Well, let's find out. Let me show you how we would do this kind of problem. The first thing that we would do is we would say we want things to be in a state of equilibrium. We want Jimmy's torque to equal Timmy's torque. If we want that to be the case, then we want the net torque to equal 0. When I'm talking net torque here and I look at this situation and I say, hey, what is involved in the net torque? I say, well, we have positive torque from Timmy and negative torque from Jimmy. And those two should cancel each other out. They should add to equal 0. Now, if we wanted to look at the size of Timmy's torque, we'd say that the size of Timmy's torque is the force that Timmy applies, which is going to be Timmy's weight, times the length of Timmy's lever arm, excuse me, sorry, minus the force that Jimmy applies, which is going to be his weight, times the length of his lever arm here, and that's going to equal 0. Now, we weren't given their weights. Oh, first of all here, do you see that we don't have to do anything with the parallels here because the line of action where the force is applied, that's already nice and parallel to the length of the lever arm, so we feel good about this situation. But so now we were not given their weights, so we got to change this into things that we do know. And we're going to change this into the mass of Timmy times G times the length of Timmy's lever arm minus the mass of Jimmy times G times the length of Jimmy's lever arm. That's going to equal 0. Now, I wasn't given any numbers for this problem, but I'm wondering, first of all, I was given an algebraic ratio here between the mass of Timmy and the mass of Jimmy. So I'm going to plug that in. And I'm going to say that the mass of Timmy, I wasn't given a number for it, but I do know that it is 2 times the mass of Jimmy times G times the length of Timmy's lever arm minus the mass of Jimmy times G times the length of Jimmy's lever arm. And now, what I'm looking for ultimately is where Timmy should stand. I'm looking for the length of Timmy's lever arm. So I can rearrange to find the length of Timmy's lever arm. And I got to move this down just a little bit. To find the length of Timmy's lever arm, I can move this over to the other side. So I get mass of Jimmy times G times the length of the lever arm for Jimmy divided by 2 times the mass of Jimmy times G. And hey, would you check it out? Our G's cancel out, the mass of Jimmy cancels out, and I'm left with that the length of Timmy's lever arm should be 1/2 times the length of Jimmy's lever arm. Hey, can you check it really quick? Why does this answer make sense? That the length of Timmy's lever arm should be 1/2 of the length of Jimmy's lever arm. Well, you say, well, Timmy has twice the weight, and if he has twice the weight, then he needs to have half the lever arm. And if he has twice the weight and half the lever arm, then his torque will equal out Jimmy's torque, and they will have the same torque, which means we'll have a state of equilibrium. Okay, there's a little work with net torque. The last question that I want to show you is a practice question from your textbook. So I'm going to get this pulled up here. This is from page 258. Let's see here. Let's go red. This is from page 258. And this is we're going to look at question number 2A. And you must excuse me because I did forget my textbook, so I'm going to pause real quick, grab my textbook, and I'll be right back with you. One moment, please. Okay, here we go. My textbook, page 258, question number 2A. It says, a simple pendulum consists of a 3.0 kilogram point mass hanging at the end of a 2.0 meter long light string that is connected to a pivot point. It says, calculate the magnitude of the torque due to the gravitational force around this pivot point when the string makes an angle of 5 degrees with the vertical. Okay. First, when it says a 3 kilogram point mass, that just means that the mass of our little bob here on the end of our pendulum is 3 kilograms. So we can write this here, that the mass of this little guy here is going to be 3.0 kilograms. Then it tells us that the length of this pendulum, which I shall call length L, is equal to 2.0 meters. And that is going to be from, whoa, not very good. Let me try again. Oh gosh, not the working wheel of death. Okay, from here to here. There's the length of my pendulum. And it says, can you calculate the magnitude of the torque when the string makes an angle of 5 degrees with the vertical? So here's the vertical. This is where our pendulum normally lives. But do you see that I've pulled this pendulum back so that it is now at an angle theta of 5 degrees from the vertical? So it's something like this. Now, do you agree that if I were to let this pendulum go, then it would swing in a nice circular arc? Now, this pendulum doesn't start spinning, but it will end up spinning if I let it go, because it will be spinning, not really spinning, but it will be carving out an arc of a circle. We say then if it started not spinning and it ends spinning, then we had some torque that happened. The torque, the force that actually makes this pendulum swing, that force is going to be the weight of the pendulum, or the force of gravity acting on this pendulum. Now, let's identify a few kind of key players on here that are going to be some important identifiers. First, let's identify where the pivot point is, or the axis of rotation. Do you agree that this whole pendulum is going to spin around this pivot point here? And so this we shall label as the pivot point. Then, my line of action. The force, which is going to be the weight or gravity is going to pull on this guy here straight down like this. So this is where my line of action is. That means that the length of my lever arm is going to be the length L, the length of the string. Now, here's the thing. We need to calculate the torque. We know that torque, let me write that as my unknown. I am looking for the torque created by gravity. And it does just ask for the magnitude of the torque, so we don't need a vector hat on here. We can just write it as torque without a vector hat is what we're looking for. Okay, now we know that torque is equal to the force that is perpendicular to the length of the lever arm times the lever arm. If you look at the length of the lever arm here and you look at the force, you'll notice that the weight is not at all right now perpendicular to the length of the lever arm. The length of the lever arm is at this angle here. So we need to break down this force into its component parts. We say that there is going to be one component of the weight, which will be nice and parallel like this. And this, or nice and perpendicular like this. And then there will be another component of the weight that is parallel to the length of my lever arm. Do you see that my lever arm goes like this? And I didn't draw this really nicely, but do you see that my lever arm goes like this? And then FG goes like this. So this is the part of FG that is parallel to my lever arm, and this is the part of FG that is actually going to cause this thing to rotate, the part that is perpendicular to my lever arm. So I am looking for the part of FG that is perpendicular to the length of the lever arm. To find that, notice I have a setup with some similar triangles here. If this angle here is theta, that means that this angle here will also be theta. So then I can say, looking at this diagram, that the part of the weight that's going to be perpendicular is going to be Fg times the sine of theta times L. Now I know that Fg is equal to mg, so I can write mg times the sine of theta times L, and now I can plug in numbers here. The mass of my little pendulum bob here is 3.0 kilograms. G, we know deep down in our hearts, is 9.81 meters per second squared. Sine of theta, we know that theta is 5.0 degrees. And then finally, the length is 2.0 meters. Plug that into your calculator, and you would get something like, oh gosh, I don't really know actually, 5.1 Newton meters, or newtons times meters. And there's your final answer. If I asked you for the direction of the torque based on the diagram that I drew here, you would say, well, that torque is going this way, which appears to be kind of sort of clockwise, and so I would call that negative torque in this case. But that's based on the way that I drew my picture. Couldn't you have also pulled the pendulum back the other way? And that is all for today, folks. Today we talked about torque. We talked about what torque is, and we defined how it's the force that's perpendicular times the length of the lever arm. We talked about a few different scenarios where you looked at different instances of torque. We talked about how you can change the size of the torque based on either changing the size of the force or changing the length of the lever arm. We also talked about other things. Oh yes, we talked about net torque and equilibrium, which happens when the sum of the torques is 0. We talked also about how to calculate torque when you had kind of a complex problem here with a nice little pendulum. And that's all for today, folks. I do hope that you have a wonderful rest of your day, and I will see you all next time. Bye, good people.